I bought these tiny 2 amp units. They say you must have closed loop to avoid lost steps. I bought a box of cheap open loop steppers, and they definitely tell it you need a massive industrial power supply to run it all. I'm running everything off this, a 5 amp power supply. So this will go into this 4-axis stepper driver rated for 20 amps, so I'm a little bit short. Most people overbuild because they're guessing. I'm going to show you a design spreadsheet that proves why these tiny specs are actually perfect for the job. And you probably don't need the monster hardware that you think you do. In fact, I'm going to prove to you that I still overbuilt with these motors, but I didn't overspend. I bought a couple of these cheap off eBay a few years ago, and after I ran the numbers through Marshall's design spreadsheet and actually used them and bought what he had. I bought a whole box, everything he had. So you can still, I've got a few left. A whole box full here. All still nicely packed in their original packaging. These motors have an ROP of $250, and I paid a song for them. So much so, by the time I bought the wiring harnesses, tiny little wiring harnesses, I'd added 50% to the purchase price. And by the time we finish, you'll appreciate the difference between a name brand stepper motor like these Sanyo Denkis and the average Chinese motor everyone else uses under the mistaken belief that a stepper is a stepper. So let's see what we know about these motors without getting too deep in the weeds yet. We know they produce 2.7 Newton meters of torque and draw 2 amps. And we're using a 48 volt power supply, and that gives us an envelope of roughly 96 watts per drive per unit. So that's 2 amps times 48 volts. So this motor will be perfectly safe without losing steps as long as we respect these 3 limits. Don't ask for loads over 2.7 Newton meters, don't require more than 96 watts of peak power, and don't exceed the voltage limits. Undervoltage will derate your system, and we don't want that. We also want to make sure it doesn't melt. Manufacturers usually rate these for around 130 degrees Celsius, so don't panic if your motor gets hot. It's allowed to burn you. Finally, we need to check the inertia ratio, the system versus the motor. We want to keep that close to 1:1. If it's much less than that, we wasted money on an oversized motor. If it's much higher, then you risk losing steps. As you can see, I still have a few left, so I thought I'd better use some. So the design decision became even easier after I found this scrap of gear rack sitting in the road here in my tiny shed. It's about 720 millimeters long, perfect for a small desktop CNC machine. I've been busy in Onshape designing a machine starting with how to mount this rack. So it's too hot in the shed here at 35 degrees Celsius, so let's go back into the air-conditioned office and run the numbers. It's a lot cooler in the air-conditioned office. Let's just go back to the goals we set earlier. We want to make sure we don't ask for loads more than 2.7 Newton meters. We don't want to ask for more than 96 watts of peak power, and we don't want to exceed the voltage limit of 48 volts. So hang about until the end of this video and check out the scorecard to see how I went in this case. In fact, I found this particularly challenging. The original spreadsheet we had, the model, was based on a plasma machine, and in that case there was no cutting forces. So by the time we added cutting forces and built in better modeling of ball screw axes, this proved to be a lot more challenging than I thought. So let's get this straight. We want to take these 4 motors with total power draw of 8 amps and attach them to a 5 amp power supply and to a 4-axis stepper driver, which is rated for 20 amps. And then we want to connect it all to a router, and we want to make sure that we never lose steps. So the model that we're using is called the work energy method, and it's more for industrial environments. But think about a machine that needs to take a cherry out onto a cupcake sitting on a conveyor belt. And it's easier for the designers to say, well, we want that cherry out there in 3 seconds. So we set time being 3 seconds across here. And this is our normal trapezoidal acceleration profile. I don't know if you've seen this before, but this is exactly how Linux CNC works and most other motion controllers works, is that there's a constant acceleration going up to the cut speed. Once we get to the cut speed, that stops out, and then it goes along, and then there's an equal deceleration phase, exactly the same as that. So these guys decided in this work energy method is that they would talk about a motion profile. So in this particular case, if that's 10%, this is a 10% motion profile. So 10% of the time will be spent accelerating, and 10% of the time will be going down here, and that leaves 80% traveling here. Now, that ends up with a very relaxed motion profile. But what we want to do in CNC, and particularly where we're plunging into material, we want to hit it hard and see what's going to happen without something breaking. So we want this to be 1 to 2%, ideally 1%, but up to 2%. So what happens then is that we set the cut speed and say we're cutting at 3,500 meters a minute, then we're going to accelerate for 1% of that time over probably a 1% or 2%, 1 second, something like that. So then once we calculate all that, we actually have this very good model of the machine, because we're following all of the acceleration, this area here where there's no cutting forces, and the only thing that's got to be dealt with is friction and gravity if it's a vertical axis. And then this here then is we've got to stop on time, so the deceleration happens in exactly the same requirement of this section here. So another percentage here. So let's, without further ado, let's then move on to our model. So here's our completed model, and you can see here we've drawn the motion profile here, and notice that we're using SI units, which stands for System International, or the metric system. Now the reason why, even though this was done by an American engineer, the reason why he chose to do this is that it simplified significantly the actual mechanics of the engineering calculations that are quite complex. And it could be converted back into appropriate units at the end of it if it had to be presented in such a way. So we've started here with, we'll look at the y-axis first, and we'll try not to spend too much time here, but anything in green is data entry. You won't find this anywhere else. This is unique to me, and with the help of an engineer, Mr. Marshall Whitney in Texas. So we've got a 60 kg gantry, 3,500 cut speed. This is not our maximum speed. This is the actual cut speed when we're doing work. And we're seeing our 1 second here. And that's saying that we'll accelerate at 4,860 millimeters per second. So 4.86 meters per second. Our motion profile here, we had to settle on 1.2%. We couldn't get it down to 1% for a number of reasons. And then we have the number of motors. So this is a gantry, so the y-axis with a motor each side, and also pinion pitch diameter. So this is the diameter in SI units, meters, of the pinion. Now, we're using a mod 1.25 gear rack, our choices became 20, 30 and 40 teeth per around the pinion. So we settled on a 60 millimeter pinion, and that seemed to be the best to suit this, where you can play around with this parameter, and then the rest of it is a gearbox. We worked on a 5-to-1 gearbox here, and on the z-axis we needed a 2-to-1 gearbox to make this work, and all the rest of it is really just friction and losses and that sort of efficiencies. And finally we get down to our cutting forces, so 150 newton meters in the x and y axis, and 600 newton meters on the plunge, and this is the one that's terribly challenging. Without further ado, we'll just go over to the results. There's a lot more stuff in here, but the results will summarize this. Once again, our motion profile 1.2s, number of motors, drive reduction ratios 5, 5 and 2, cutting forces, and then we get into the meat and potatoes now. We've got 93 RPM at the motor to achieve the 3500 I didn't mention that, but 3,500 millimeters per second cutting in X and Y, and 800 millimeters per second plunge. So then we've got something along the lines of 4.86 meters per second in the acceleration. 953 here. So factoring that down, we start getting into things here now. So the maximum no load, this is our rapids, could be 28,274, but we're going to adopt a more conservative 20,000 millimeters per minute. And on the z-axis, same thing. We're saying maximum 1,600 millimeters per second, and with no load, and we're going to set that to 1,500. So we just round it off and provide a bit of a cushion. So a little bit more. This one's an important ratio. This shows that we've got a perfect match between the system inertia and the rotor inertia in the motor. So the ideal is to get that to 1-to-1. Anything more than that is a bit dubious, and anything less than that says we possibly wasted our money because we've over purchased. So, and the z-axis is constrained significantly by the plunge, and you can see it's a very not a very efficient motor. So then we get down into what our voltage is. We've got 48 volts at every motor from that one power supply, and the average power that we're using. Yep, we achieved our goal here. Look, it didn't exceed 96 watts, so that's good. RMS is at more of an average, and we calculate the resonance frequency so that you don't get excessive vibration. So we want to stay out of this range here. So then we have a look here. We've got 1.4 amps peak, 1.8 and 2.3 on the Z. So we're a little bit over here on the Z, but it's only for a small period of time. So, and when we're sizing things, in any case, we work on root mean square RMS amps, so that only comes down to 1.2. So, but this is the one that was a bit of a challenge. So the first X and Y are really easy to manage in a 48 volt power supply because they only need 17 volts to achieve what's required. But this Z-axis requires 51 volts, and we've only got 48. So that results in a 5.6% efficiency reduction. Now, what that means, instead of having our 2.7 newton meters of torque, that's reduced by 5.6% to 2.55 newton meters. But if we go back up to our model, I think I had that here. We only need 1.88 Newton meters. So what we're saying is that we can achieve 1.88 Newton meters without any issue, even after having a 5% decrease in reduction on the actual performance. And finally, we calculate the ambient temperatures. So ambient temperature is 35 degrees. So the highest we see is 44 degrees, which is really 9 degrees C, which is nothing really in terms of what a stepper motor can do. So then we better look at some theoretical maximums for Linux CNC. We said 28 meters per minute, 1600 millimeters per minute on the Z, and we then will adopt these slightly lower figures here to be a little bit more conservative, to provide some headroom, and then to feed this back into millimeters per minute, converting it back to millimeters per second. We have these numbers here ready to plug straight into your Linux CNC ini file. So let's have a look at the power supply. The ideal power supply should have 200 watts. We've got 240, so we've got a 17% headroom here. The actual peak is 204, which is under 240. The minimum power supply voltage is 51, so we've lost that here, but we're saying that that's okay because of the performance we want. So, and we need 5.6 volts. Now that's more than the 5 volts that we've got on our power supply, but we know in the industry that we can uprate power supplies for CNC use because it's not constant by about 140%. So this number here is under our 7 amps, 40% increase, and you can see data to that effect on sites like Gecko. So everything seems to be done. We're just no drivers exceed their torque specifications. X and Y motors do not exceed the power budget. Z exceeds it marginally. X and Y motors do not exceed our voltage limit, but Z exceeds it by a little bit, and this results in a torque reduction which doesn't impact performance of the system. So the motion profile has been increased from 1% to 1.2% to ensure acceleration can be met from known performance. And the system rotor to inertia ratio is okay. 5.6 amps is okay. Thermal energy is okay. And we'll just mention that the Z-axis is the critical path. And we mentioned that before. So the demand of 600 Newton meters requires 2.1 Newton meters, and we mitigated this by adding a 2-to-1 gearbox, and it still didn't meet demand, but it worked out in the end. So and I just wanted to then talk about the limits here. One of the things we wanted to have a look at was compare this with the torque curve for this motor, and the torque curve is based on 24 volts. So this is the 24 volt failure zone. So if you increase, if you work at 24 volts, this would never work. But at 48 volts, we've actually got some headroom. So we have the ramping energy here at the 1.2%. So that's on the entry. And then at 600 Newton meters peak plunge. And then it settles back down again. So all in all, we've got this well covered. So how did we go? Did we pass? We do offer this as a paid service, so if you go over to our Ko-Fi site, and there's a link in the description, then you can ask us to review your motor selection or actually assist with a motor selection, so that a little bit of money spent up front now might save you a lot of time, money and effort in the future. So Thanks very much for watching and have a great day.